Vado? Ok. Okay, so I think we can start. Well, thanks for being here again. So this is the one but last lecture. So today I'll be talking about signal processing. So I'll talk about the sensitivity of gravitational wave detectors. So we'll try to derive for you the signal-to-noise ratio, optimal signal-to-noise ratio of a gravitational wave signal. And I'll go on and derive the Fisher matrix, which I believe you have seen yesterday in an exercise, but I'll go through that again. I'm not sure whether Andrea derived it in full detail. Before we do this, however, I wanted to correct this factor 2 that yesterday I was getting wrong. You remember at some point I was worried about the factor 2, and I said maybe what I called, for those of you who were here yesterday, I said that tau was the round trip time. I was trying to derive the antenna transfer function. So we had this laser going back and forth between 2 points, and the round trip laser travel time, round trip laser travel time is given by tau, L being the length. So, and I was trying to derive an effective expression for the gravitational wave strain, including the transfer function. So, and what I wrote, and this is where I had factor 2 missing, I was saying the phase difference between the signal, the phase difference in the laser, the difference of phase of the laser induced by the passage of a gravitational wave, I wrote was delta phi laser, if you want, equals minus dl 2 pi nu, where nu was the frequency of the laser, remember, divided by c. And dl was the change in length induced by a gravitational wave, 1/2 h, h being the strain. And where I was missing the factor 2 was here, because of course what you measure is the phase difference at this, so if you have a LIGO detector or a Lisa-like detector, you measure the phase difference between laser 1 and laser 2 at this vertex. So the laser needs to go, well, to go through an outbound journey and then go back. So what you have here is a factor 2, essentially, because it's the phase difference in a round trip. Okay, so this accounts for the factor 2, and let me write well, I wrote it yesterday, modulo this factor 2. The final result is the response of a detector. This is probably one of the last things I wrote yesterday, is given by h of t equals some detector tensor dij contracted with hij tt, this being the object we've been computing in the beginning of these lectures through the quadruple formula, essentially, times a transfer function, t, which is usually expressed in the frequency domain. So let me write tf. If you have several frequencies, of course, you need to integrate over different frequencies. And this dij was 1/2 ui uj minus vi vj, where this u and v are unit norm vectors that define the arms of your interferometer. And this transfer function tf, remember, was sine of 2 pi f tau, where tau is again the round trip travel time of the laser divided by 2 pi f tau. And in particular, in the low frequency limit, for f going to 0, if you want, this goes to 1. So this is why normally you don't see this transfer function in textbooks, where you're only concerned with this 1/2 h term. So today I want to go a step forward and discuss the instrumental noise a little bit. So as most of you I'm sure have heard, gravitational wave detectors are very noisy in the sense that this is a very sensitive, if you take the quadruple formula that we derived and calculate what is the this change in length, delta L over L, that you expect for a gravitational wave detector, that's tiny. That's less than the size of a proton. So you need to resort to laser interferometry. And, but still, it's a very challenging measurement. So there are a number of sources of noise that I will discuss. But what do I mean by noise first? So this is what you would expect, the output of the detector as you would expect it if you just had a gravitational wave. What we have in practice is something different. This is the output of a detector. S stands for signal of t equals h of t, where h of t is given exactly by that formula, plus some perturbation, some noise, some error, some instrumental noise. This is what we call the noise. So in practice, you can think of, if you want a small gravitational wave, like a sine or a cosine, and then on top of this, you have noise, really. And you can, the purpose of gravitational wave data analysis or gravitational wave detection is to extract this small signal inside the noise. First of all, let me say, however, before I go into how we can extract the signal, let me say a few words on what this noise, how we describe the noise. So it's let me erase this sorry figure. And so normally we characterize the noise not in the time domain, but in the frequency domain. So we define what we call the power spectrum of the noise, or noise spectral density, sometimes called. So we define the Fourier transform. So first of all, we define the Fourier transform as usually in, this is motivated from engineering. So we define it in the following way. So this n of t exponential of minus 2 pi I f t in dt. This is how we define the Fourier transform. Sometimes I will not put, in principle, I should put a tilde here to denote the Fourier transform. Sometimes I will just forget and just write n of f as just to lighten the notation. So this is the definition why we put the factors 2 pi I here. Well, because then n of t is simply given by n of f e 2 pi I f t in dt. So it's convenient because you have no prefactors in the Fourier transform. And then what we do to define the noise spectral density is to define, I guess I can write here, and then I'll say what this average means. N tilde of conjugated of f, because now the Fourier transform, even though n is real, is going to be a complex function. N of f average is an ensemble average. I will explain what it means. 1/2 s, and I'm running out of space here, sorry, times, let me write here, delta f minus f prime. So if some of you are cosmologists, you will recognize the usual definition of power spectrum in cosmology. This is exactly the same definition, although of course it's a slightly different quantity. So first of all, what is this average? So this average is what we call an ensemble average. So this noise is a random process. So ideally, if we have several parallel universes in which the noise were realized in different ways, we would take the average over all these realizations of the noise. In practice, since we just have one universe, of course, that we know of, what we do is to take a time average, so average over time. So, and why? This is because of something called the Ergodic Theorem that tells you that an ensemble average is the same as a time average. You can understand this by thinking of, what is the example that people make? Yeah, birds, for instance. So suppose you know that that birds spend 99% of their time in the air, you would expect at any given time that one bird out of 100 were on the ground. So to measure, so if you want, you gain information on the whole population of birds, the ensemble average, based on a time average. On average, in time, how many birds are in the air. And this is the same as what we do here. This is the same as what you do in cosmology. When you study the theory of inflation, you have a bunch of averages which are ensemble averages, which, in fact, in cosmology approximate as spatial averages when you measure the power spectrum. When you measure the power spectrum in cosmology, you take a sky map and you average over spatially over our single realization of the universe, but what you get from the theory is actually an ensemble average. So the same is here. So we have just one universe, so we take, we can't perform ensemble averages, but we can perform time averages. So we can divide our noise in different batches, if you want, take Fourier transforms and calculate what this is, and then average over all realization, over all chunks of the time series. Okay, so how about this delta f minus f prime? Again, this is the same as you find in cosmology. In cosmology, well, I don't want to put myself on the spot and write something wrong, but you have the power spectrum, so you have something like the power spectrum of, I don't know, the density is defined as rho k prime, and then there are some factors, so let me write proportion of p of k, delta k minus k prime, something like that, with some prefactors that I don't remember now. And this k minus k prime comes from the homogeneity of the universe. Here, the delta f minus f prime comes from the fact that the noise is stationary. So let me show you this. So what I want to do, I can write here. I want to show that stationarity of the noise is responsible for that Dirac delta in there. So let me just take the definition of Fourier transform and try to calculate this average. This is n of f times n of f prime. And then I just take the definition, integral. So I have two integrals, dt prime, because I have n of t, n of t prime. What sign did I use? E minus 2 pi I f t plus, sorry. Oh no, I have a complex conjugate, so here I have a plus, I think, yeah, and then I have a minus 2 pi I f prime t prime, and then average, right? And then, so I'm thinking of this as I said, an ensemble average, although in practice it becomes a time average. So I can swap, I can commute this average with the integral sign. Integrals are nothing but a sum, of course. So I have n of t prime, e to the 2 pi, let me write it, yeah, minus 2 pi I f prime t prime minus f of t. And here, sorry, the average is close here, dt, oh, I wrote the dt and t prime there. So now, let me change variables. Let me introduce a time difference, delta t equals, so what do I want to write it? Well, delta t equals t prime minus t. So this integral becomes integral, I keep the dt. Sorry, I keep the, in fact, let me write d t prime, and then I write the average of n of what do I want to write? T prime. Well, I keep t equals t prime minus delta t, and then I want to keep n t prime averaged, and then I have times the exponential minus 2 pi I f prime t prime minus f multiplies t prime, but also plus t prime plus f delta t. So, yeah, good. And in fact, let me write this in a slightly different way. Let me write this here, exponential of minus 2 pi I f delta t. So I get rid of this. And this I can collect t prime, f prime minus f t prime. And then what I can do is yeah, there is something that yeah, in fact, sorry, here I wanted to do the integration in, I want to swap, I want to keep t here, and I want to write, yeah, so I want to write the integration as, I want to keep as my variable delta t and t. And then what I, sorry, I'm confused about it. Sorry, just a second, I'm confused about something. Ah, yeah, so that's why I didn't get it. So now I want to make the assumption that the noise is stationary, right? So I want to make the assumption that the noise is stationary, which is the crucial assumption. That's why I couldn't get the result. Stationary noise. Let me write there. Stationary noise. Stationary noise. So stationary noise means that there is no preferred time. It's the same as homogeneity in cosmology. So that means that the average of n of t times, sorry, yeah, that quantity there, n t prime minus delta t equals n of t prime. I call it a function of delta t alone. So this average doesn't depend on the particular point, t prime, on which I'm doing the calculation, but just on the difference between the two times. This is what we mean by stationarity of the noise, that the noise is not necessarily uncorrelated in time. So the value of the noise at t is correlated in principle with the noise at t prime minus delta t, but this correlation is only a function of the distance between the 2 points. So if I keep doing that integral, so I keep writing here, I get the delta t, d t, and then here I have some function f of delta t, and then I have exponential of minus 2 pi I f delta t, and then I have some exponential of minus 2 pi I f minus f prime of t prime, and then, in fact, sorry, yeah, so this should have been it, sorry, I correct myself again, this should be a t prime, because I want to do the integration in t prime. Yeah, so when I changed variables, I kept t prime, and then I want to swap t with delta t, but then I probably have a minus sign here. Sorry about that. Well, anyway, so I have a minus sign here, and then I have an integration over t prime. Now, the only term that depends on t prime is this term here. So you will recognize that this is nothing but the Fourier transform of the delta, right? So by integrating the exponential minus f and f prime in t prime, you get a Dirac delta. So modulo and minus sign that I might have messed up, what you get is integral in delta tau, f of delta t, exponential minus 2f pi minus 2 pi I f delta t, and then here you get a delta f minus f prime, right? So this is exactly the delta. Did I delete it? Yeah, I think I might have deleted. So what I was trying to derive was the definition of power spectral density of the noise, so which I will rewrite because I deleted, n of f, n of f prime, there are tildes there, equals 1/2 Sn of f delta f minus f prime. So you see that this delta f minus f prime arises from the stationarity of the noise, whereas this here is what we call sometimes the sensitivity, but more in more technical terms is what we call a single-sided noise spectral density. Noise spectral density. Okay. This is what we call sometimes sensitivity. Why single-sided? Because we have a factor 1/2, and single-sided because if you then try to compute what the average over of n squared of t is over an ensemble, if you use this expression and the definition, of course, of Fourier integrals, you find integral from 0 to infinity of Sn of f. So this, if you want, this Sn tells you how much power there is in the noise. So if you want to compute the root mean square value of the noise, of course, the average of the noise will always be 0, pretty much by definition. But the square of the noise, when averaged over the ensemble, will not be 0. And if you use this definition, we'll find that it will be the integral from 0 to infinity of the single-sided noise spectral density. Henceforth, the name single-sided, because it's an integral from 0 to infinity. It's not an integral over negative frequencies. Okay, so at this point, in an ideal world, I will show you a few pictures of the noise, but and then I would go back to the blackboard, but maybe I'll try to draw things on the blackboard. So what is this detector noise really made of? So what is it physically? So this depends very much on the kind of detector that you consider. So for LIGO, so I'm going to try to write on the blackboard, you can take, so what are the dimensions of that Sn are, of course, as you see from there, because the noise is dimensionless, because you remember S equals H plus noise, although my H and N's are very similar, sorry. So S is the signal, H is the strain. The strain carries no dimension, so N carries no dimension, and therefore the dimensions of Sn are 1 over a frequency. You see it from that expression. So sometimes people take the square root of Sn, and this has the dimensions of 1 over a hertz, the square root of a hertz, to the minus 1/2. This is what you see sometimes plotted in figures, and namely in the figure that I will be trying to reproduce on the blackboard. This is the noise spectral density of LIGO, or actually what we call, and this is called the strain sometimes, the square root. This is what people, the noise, they call the noise strain sometimes. So frequency in hertz, square root of Sn in hertz to the -1/2. Say this is log scale, so 10 to the 2 hertz, 10 to the 3 hertz. This is what LIGO sort of looks like. Yeah, well, the shape of the bucket here depends on various things. So essentially, yeah, this is what the sensitivity of LIGO looks like. So it has a most, so the lowest this Sn is, the more sensitive the detector is. So for LIGO, it's at is about 100 hertz, a few hundred hertz. And what is the noise due to? So at low frequencies, so let's say in this, I don't know, in this region here, the main source of noise, let me call this zone 1, zone 2, zone 2, zone 3. In zone 1, the main source of the noise is, well, there are various sources. Depending on the sensitivity, you have seismic noise, Newtonian noise, and then I will explain what these are. And I think for certain configurations, yeah, also the shot noise becomes important. The shot noise, and I will explain what the shot noise is. In zone 2, the bucket is essentially given by the shot noise of the laser. And at high frequencies, for LIGO, it's given again by the shot noise and also the antenna transfer function we talked about yesterday. Shot noise and transfer function. Transfer function. So actually, let's start from seismic noise. So it's very difficult on Earth to go beyond or to go below a few tenths of hertz. So this could be at 10 hertz. So certainly LIGO cannot go beyond 10 hertz. And this is due exactly to this seismic noise. So which means not only earthquakes. Fortunately, big earthquakes are not that frequent, but there is a low frequency humming by the Earth to which gravitational wave detectors are sensitive. So it's really that plus anthropic activity. So trucks passing by, people walking, the ocean waves or the sea waves in Virgo. This is one of the things that they see, even though Virgo is like, I don't know how far it is from the sea, a few, maybe 20 kilometers. So to overcome this, well, there is another source of noise, which is important here, which is the laser shot noise. And this is a quantum effect. So normally we think of lasers as electromagnetic waves, but actually they're made of photons. And so this has to do with the fact that light is quantized, if you want. So there is a Poissonian square root of n error on the square root of n oscillations or uncertainties in the number of photons that reach the mirror at any given time. And of course, when you're at very large, when you have a very large number of photons, this uncertainty, this Poissonian error is negligible. When you have few photons, that's a problem. And since the two detectors are the mirrors are kilometers apart, this can become a problem. Of course, the power of the detector, but you would heat the mirrors up. So this would cause another source of noise, which should be here, but in the figure for static noise, yeah. So there's also another sort of noise, which is the thermal noise of the mirrors, because you can increase the laser to decrease the shot noise, but then you deform the mirrors, so you heat them up, you have thermal noise, and so on and so forth. So this is the shot noise. The shot noise is active everywhere, and in particular it's responsible for the bucket, so the, if you want, the minimum or the maximum of the sensitivity or the minimum of the power spectral density. And it's also active at high frequencies. Let me say, however, a few more words about the Newtonian noise. One of the things that I wanted to show this afternoon, or maybe later in this lecture, is that there are several gravitational wave detectors that are planned to go beyond LIGO and Virgo. One of them is LISA, to which I alluded yesterday. The other one are so-called third-generation gravitational wave detectors. There is a planned detector in Europe called the Einstein telescope. There would be a detector in the US probably, which will go under the name of Cosmic Explorer or something like that. The name hasn't been decided, the site neither, nor the specs. But the idea is that these detectors will be much longer in order to be, because the length of the instrument also affects the sensitivity. Why? Because of what I wrote before, that the H that you can measure, or if you want, delta L is 1/2 HL. So if you want a larger delta L for a given strain, you can just increase the length. This is one possibility. But also they would go underground, probably. At least the European one. I'm not sure about the US one. The European one is planned to go underground, maybe in Sardinia, maybe in the Netherlands, and in order to cut this seismic noise, because seismic waves travel on the surface, apparently, or at least the waves that they care about, and also to decrease the impact of anthropic activity. And then there is another source of noise, which will become important, which is the Newtonian noise. So, and that is not just seismic activity, it's really seismic waves traveling on the crust of the Earth. And what these detectors will become sensitive to is the gravitational pull of the underdensities and underdensity, overdensities of these waves that these waves cause in the crust of the Earth. And so these underdensities and overdensities will pull just by Newtonian attraction the test masses or the mirrors, and it will cause another source of noise, which is called Newtonian noise. So this means that maybe with third-generation detectors, we'll be able to go down to 1 Hertz. So this could be, I'm not sure about the scale, but this will be ET. So at low frequency, it will go to much lower frequencies, but it will never be able to go below 1 Hertz. What they're trying to do is also to install seismographers around the sites of gravitational wave detectors. Like in Virgo, they're putting seismographers around the site to measure the seismic waves and subtract the effect of this Newtonian noise. So they're not yet at the sensitivity at which this is a very important problem, but they're doing that to prepare for the third generation gravitational wave detector. So these detectors will also be cryogenic. In order to decrease the thermal noise of the mirrors. And they might also use squeezed light, so particular quantum states for the lasers in order to decrease the shot noise. So these are the next steps, if you want, in ground-based gravitational wave physics to cut the seismic noise by going underground, the Newtonian noise by subtraction using seismographers, shot noise using squeezed light. As far as the transfer function is concerned, this is what we derived yesterday, which I deleted, of course. You remember that there was this transfer function, which is sine of 2 pi f tau, where tau is essentially the length of the detector, f of tau. And I was telling yesterday that this transfer function, when the frequency is large, goes as 1 over f, because this, sine is bounded, and you have 1 over f here. And this is exactly why you have this tail in the sensitivity that increases proportionally to f in these units. So this s is the square root of the strain. So you get, so this s is actually the strain. So this is proportion to f. And how do you improve this? Well, you have this factor here, tau, which is the length, the light travel time the round-trip travel time of the laser, so you increase that. So you improve this by having a larger detector, if you want. And this is why next generation detectors will be probably 40 kilometers long in Europe. In the US, they're talking even about 100 kilometers, although it will not be a cryogenic detector. What time is it? Okay. So I will also, well, I talked about LISA yesterday. Well, since I'm discussing the noise, I will also discuss the noise budget by LISA. LISA is a space-based Michelson-Morley interferometer. So this is the sun, this is the Earth traveling around the sun. LISA is a triangular-shaped, equilateral triangular-shaped interferometer trailing the Earth around the sun at about 15, 20 degrees. It still has to be decided. And the length of the arms will be about 2.5 million kilometers, gigameters. So it's actually two independent Michelson-Morley interferometers. So you can think this is, for instance, this is one independent interferometer, and for instance, in one of the other two combinations this could be another independent interferometer. And the third interferometer that you can get is actually not independent of the other two. So you can think of LISA as two LIGOs in the sky in a certain sense, in a very rough sense. So what is the noise budget for LISA? So first of all, we want to go to space to overcome the seismic noise. There is no seismic noise nor anthropic activity in space. So the main cause of error, if you want, the loss of sensitivity for LISA is, in fact, the capability or lack thereof of lack of capability of putting mirrors or test masses in free fall in space. So this is why the sensitivity curves looks like this, with a few. So the bucket is at few millihertz. So zone 1, zone 2, zone 3, very quick here. So in zone 1, this is the acceleration noise, radiation and thermal noise, and thermal noise. So essentially, it's so LISA is made of there are spacecrafts, of course, that contain not really mirrors, but test masses, which are put in ideally in free fall. But there are a number of reasons why these test masses are not really in free fall, because there's solar wind, there are electric charges, there are thermal fluctuations, because they, in the same way in which in LIGO you have thermal fluctuations. So this acceleration noise is due to the difficulty of putting these test masses in free fall, due again to electrostatic charges, solar wind, etc. And this was tested with an experiment called LISA Pathfinder, which flew in 2015. So we have a pretty good idea what the low part of the sensitivity curve is. You have thermal noise for the test masses, similarly. In 2, you have, well, again, the laser shot noise, which is very important because the detectors are 2.5 million kilometers apart. So there are very few photons that reach the other end of the detector. So if you start, I think it's 2 watt, I forgot the power of the laser, but many photons are lost in the way. So to go from one arm to the detector to the other. So shot noise is a problem. Of course, you can't again increase the power of the laser too much, because then you hit the thermal noise. And in 3, this is really the transfer function. This is exactly what we discussed yesterday, the same as in LIGO. So again, here you have a 1 over f behavior, and you have some oscillations here, which are due to this sign that oscillates, and also to the fact that the constellation rotates around the Earth, and is not, so it rotates. So there is some effect from the orbit. What do I want to say? I wanted to say something else. Oh, yes, and there is also, in 1, what we call sometimes an astrophysical noise, plus astro. So in the Lisa band, there are so many sources, in particular galactic sources, that you can't distinguish them singularly. And they cause what is called sometimes a confusion noise, or if you want, it's a stochastic background. So there are so many sources. You can think of them as a foreground if you're a cosmologist. It's the same for us. They are a background or a foreground of so many sources in the galaxy that I should degrade the sensitivity of the instrument in the frequency region of sub-millihertz, certainly. Not sure about the exact frequency. Plus astro, and this is galactic binaries, binaries of white dwarfs in the galaxy. We expect that there will be 100,000 maybe of those in the data, not of them resolvable. There will be about 10,000 which are resolvable, but most of them will not. Okay, so this is just to give you a feeling of what is the physics of this noise. So there is a huge, this is one, I mean, I doubt very many of you are experimentalists, but this is the bread and butter of those who work on the instrument, to try to decrease, to find this noise budget, to understand this noise budget, and try to decrease it. So what I want to say next is as I promised, is to try to explain to you how, in spite of this noise, we can extract the signal. So again, I write this equation, very simple equation, S of t signal, this is the detector output, N of t is the noise, plus H of t, which is the signal. So how do you do it? So at cartoon level, I've already showed you that this is, we can think of a monochromatic signal plus some wildly varying noise. So plus some random numbers, if you want. So what you can do in Python, I don't know what you use in Mathematica, it's very easy to try to simulate a very simple toy model in which you have a sine or cosine in the time domain, and you superimpose random numbers, pseudo-random numbers generated with your favorite library. And then you wouldn't see, of course, the sine or the cosine, because you will have just a very large noise. And then what you can try to do is to take the Fourier transform of the time series that you obtain this way. If you've never done it, you should do it. It makes you understand what match filtering is. So in the time domain, you wouldn't be able to see the effect, but if you do the Fourier transform of your function, what you will find is that there is, of course, there will be a very noisy floor, and then you'll have peaks at the frequency, at plus and minus the frequency of the signal, depending on how you define the Fourier transform, or if you define it, or the peak at the frequency of the signal. This is how you can extract a sinusoid buried in a random noise. So you can do this in 5 minutes, and this is exactly what this is sort of what we do. Here. This is the idea behind match filtering. So what is the idea? Let me transition to these notes. Yeah. So essentially, what you want to do is to take your signal there. Well, in fact, what you do in Fourier transform is you take your signal and you multiply by usual minus the usual exponential, and you do the integral in time. So in a sense, you multiply your signal by a filter. This is what we would call a filter. And you do the integration. And if the frequency of this filter is the right one, you get a very large output. Whereas if the frequency is small, this integral essentially cancels out. So this is what we do in practice. So suppose we believe that a signal of the form h of t, so if we believe S of t contains a signal of which we know the form, and we believe it's h of t, what you can do is simply to take the product of S of t with the signal, which we call sometimes template, that we believe should be in the data, and just integrate over time. Right? You can take an average if you want. Yeah, say we take an average. And then suppose your h of t that you believe is hidden in the data actually matches what's actually in the data. So what you got here is 1 over t. I'm using that equation there. H squared of t in dt plus 1 over t h of t times what, n of t in dt. So now if this signal, so typically gravitational wave signals are oscillating, so if I were to take the integral of h of t alone, this would give 0, but because here I have h squared, this averages, this typically is of order, this integral typically grows linearly in the integration domain. So this whole factor is of order 1. Whereas this integral here, being the integral between the noise, which is a random process, and h of t, typically grows as square root of t. And because you have a factor there, overall, this goes as 1 over the square root of t. This is like a random walk. So if you integrate for a sufficiently long time, and if h matches what is actually, if your template matches what's actually in the data, then simply by integrating for a sufficiently long time, you get what we call an overlap. You get an integral which is of order 1. Whereas if h doesn't match the data, you'll get something that goes to 0 as 1 over the square root of the integration time. In fact, we can make this, is this clear? Are there any questions? No. Okay, so we can make this slightly more formal. Make this slightly more formal and prove what is called the optimal filter theorem. I think it's called also Wiener theorem. So it's something that the engineers, they're probably very well aware that they use all the time. That optimal filter theorem. So what I want to do is exactly follow this idea. Suppose I have a signal again. I'm writing this for, again, n of t noise plus some gravitational wave signal. And I want to calculate the integral. Suppose I don't know what's in the signal, so I just calculate the integral of s of t with some filter, k of t, which I don't know anything about yet. This integral from minus infinity to plus infinity. Right. And this is, let me call it S bar. And I want to define what is called, I want to define a signal to noise ratio. So I want to define the ratio between S when signal is present signal is present, divided by this S, the output of this filter, when no signal is present. No signal is present. And this is what we call the signal to noise, sometimes S over N, signal to noise ratio. And I want to find the filter, find K of t, the filter K of t, such that S over N is maximum. So based on our example there, the Fourier transform, if I have a monochromatic wave, the optimal filter here is intuitive, will be a sine or cosine. So we want to find this more in general. So let me start by computing the numerator of this signal to noise ratio. Oops, should hurry up a little bit. So I want to compute the numerator, which I call there S. So S is again the, let me call the S will be the, let me take an average over the ensemble. The ensemble of S hat, so big S, sorry, the, should use different symbols. This should be a capital S, let me call it, whatever. Let me call this SNR, signal to noise ratio, to avoid confusion. So the SNR would be the average over the ensembles of S hat when no signal, when the signal is present, okay, when H is different than 0, divided by the, well, let's compute the numerator for the moment, because in fact it's as I will explain later why. This is what we want to compute. So numerator first. I want to compute S hat when the signal is present. So in particular, and I want to take an ensemble average just to simplify things. So what is this? So so S is defined there. So it's the integral of S of t, K of t in dt. And I want to take an ensemble average. So here the filter is constant. It doesn't depend on the realization. So the only thing that depends on the realization is S. Okay? So now, what is the expectation value of S? It's the expectation value of H plus the expectation value of N. And clearly, the expectation value of the noise is 0. So expectation value of S is H. So here, the numerator is quite simple. So it's the integral of H of t times K of t in dt. And then I can use what is called Parseval theorem, or I can use simply the definition of Fourier transform and remember the representation of the delta in terms of sines and cosines, and this becomes the integral between h of f, Fourier transform, times k tilde star f. Right. And this is my numerator. So I want now to compute the denominator. Let me erase here. So the denominator would be the value of S when no signal is present. So when no signal is present, S by definition is N of t times K of t in dt. So if I were to take just the average of S, this would give 0 because the noise has 0 expectation value. Because so what I want to do is therefore take the RMS of S. So I want to take the average of s squared. So, and then take the, yes, I want to take average of this. What do I want to, yeah. So in dt prime n of t prime k of t prime, and then I need to take the average, so the average applies to this, to the noise. And then I use my definition, well, then I need to use the Fourier transform, dt prime. Then I can express this n of t in terms of their Fourier transform. So let me, so when you do the, without writing too many passages, the result that you get is n of f prime the exponential of 2 pi I ft minus 2 pi I f prime t prime. And here, because I introduced the Fourier transforms, I also have integrals in dt prime, df prime. Okay, so I've just replaced the definition of Fourier transform in n of t and in n of t prime, so I get extra integrals, so this looks like a mess. But then I can remember the definition of one-sided power spectral density, so this quantity is 1/2 Sn of f delta f minus f prime. This is the first, one of the first equations I wrote today. It's still up there. And then, so you can eliminate the integral in, you can make f equals to f prime by doing, because of this delta. And then, you need to use the representation of the, well, let's do it. Let's see what happens. Right up here. Let's try to do it quickly. So this, I'll continue on this side, sorry. So you have dt prime, df, because one of the f's has gone away, because of the Dirac delta, as f exponential of 2 pi I, now f equals f prime, so it's t minus t prime, okay. And then what do I want to get? I want to get to just an integral in frequency, yeah, and I still have the filters, which I forgot here, k of t prime. And in fact now, because, yes, k of t prime, and then what I want to do, okay, and then this becomes, I need to introduce also the Fourier transforms of the, I'm afraid of the, k of t prime. Yeah, I need to introduce the Fourier transforms of the k of f. Well, in fact, yeah, I can recognize now the Fourier transform of k. So, yeah, I don't need to introduce anything. So this becomes integral in df of 1/2 s of n of f. And then this becomes the integral in dt of k of t e to the minus 2 pi I f t, integral in dt prime of k t prime, exponential of 2 pi I f t prime. And these are just the Fourier transforms of k dt. So I got the final result, d of f. And amazingly, I also got, so the factors are all right. df Sn of f. And here I have k tilde f, k tilde conjugate f. And this, let me write as the norm, the absolute value squared. Okay. So we calculated also the denominator of this integral. And we now almost proved the theorem, so let me put things together. So the signal-to-noise ratio, to hurry up a little bit. So summarizing, S and R equals, where did we write it? We wrote it there. One is the integral of, or copy from here, h of f tilde k bar, k tilde star of f integrated in the frequency domain, divided by what we just derived on the other side. What we derived here was the average of s squared, so we need to take a square root, I'm afraid. So square root of integral in df, 1/2 Sn of f, norm of kf tilde squared. Okay, so this is our signal-to-noise ratio. So now remember, the problem that we want to solve is to find the filter k of f, which gives the maximum value for this signal-to-noise ratio. So it's convenient to define the internal product between two functions, a and b, and this is just a definition which I believe you've seen yesterday, as the real part of the integral from -infinity to infinity of a tilde star f times b tilde f divided by 1/2 Sn f, or, which is equivalent to 4 integral in df, a tilde star f b tilde f divided by Sn. This is an internal product that you find all the time in gravitational wave physics for real part. So this is just a definition of this stage, and using the fact that both h and if these functions are this equivalence, actually, if you want to show it, uses the fact that a and b are real. And therefore, for instance, a tilde, so this becomes an integral from 0 to plus infinity. So you can either write it as a two-sided integral or a one-sided integral. And in order to show the equivalence between these two, you need to use the fact that a and b are real. But this is a detail if you want. So why do I want to introduce this internal product? Well, because it allows me to write that signal-to-noise ratio in a very simple way. You can show that if you use the definition of the S and R equals the internal product of some function u, which I will now define, with h divided by u internal product with u. So the norm of u, square root, with u defined, well, it needs to, of course, to depend on the filter, 1/2 Sn of f, k tilde f. If you don't believe me, just you can do the math and keep track of the signs, etc. So these integrals are all, I think, one-sided. So I was a bit imprecise here. So these integrals Yeah, sorry, these integrals are two-sided from minus infinity. If you look at the derivation, you will find that these integrals are two-sided. So essentially what you find that the signal-to-noise ratio that we were seeking is the internal product of a function times a unit norm. You can think of this as the internal product of two vectors. So a vector h projected on a vector u divided by its norm, right? So, and this vector u is simply given by the filter that we're seeking and the one-sided noise spectral density. So clearly when you have the projection between two vectors, if you want to maximize the projection between two vectors, you need to have them parallel. So the filter k that maximizes the signal-to-noise ratio is one for which u tilde of f is proportional to h of f. So if you want, then if you replace this expression, it means that k tilde of f is proportional to h, there is a tilde here, h tilde of f divided by k tilde, k tilde, Sn, yeah, Sn of f. This is the final result. This is what we call the optimal filter theorem. So we started asking the question, what is the optimal filter by which I need to multiply my signal in the time domain and extract the gravitational wave, forgetting about the noise. So remember, we want the filter is defined as the, so I have an output of the detector S of t, and I want to multiply this output by a filter k of t, which allows me to extract the signal. And this is, again, the same thing we did for the Fourier transform. So if the signal is monochromatic and there is no sensitivity, and if there were just a white noise with Sn constant, the optimal filter would be simply the sine and cosine. So here what the theorem tells us, and in this sense it generalizes the Fourier transform example I made, is that the filter by which you need to multiply your signal is given by which you need to multiply the output of the detector, is given by the signal that you believe should be in the data, in the frequency domain, divided by the sensitivity of the instrument. So this is why it's, if you want, and this will give you an optimal signal-to-noise ratio. This will be the maximum signal-to-noise ratio that you can ever achieve. So if because of systematic errors or because you don't understand the physics, because you can't solve the Einstein equations, you don't get the correct, or you don't get a good template, this is what we call a template, your signal-to-noise ratio will be decreased. So this is why much of the research in gravitational physics today has to do with predicting what the signal is. For instance, for two black holes, producing waveforms for a system of two black holes on a computer using numerical relativity, because if you don't get those waveforms right, you will not achieve this, you will not be able to produce this optimal filter to extract the signal from the data. And in fact, your signal-to-noise ratio will be decreased. So, but suppose we know what this waveform is. Suppose our templates are exact. So suppose we can solve Einstein equations on a computer with infinite accuracy and precision. The signal-to-noise ratio that you get, S and R, the optimal signal-to-noise ratio, is the expression that you probably saw yesterday for integral from 0 to plus infinity in df h of f tilde squared divided by Sn of f. This is your optimal signal-to-noise ratio. And this comes, again, from replacing this result into that internal product. So in fact, you can write this as also more simply using the internal product definition that we wrote there as the norm of H. So using that internal product, the signal-to-noise ratio, the optimal signal-to-noise ratio, SNR optimal, will be given by 1/2, the norm of H. So this took much more than I anticipated. So in practice, this allows you to compute the signal-to-noise ratio for any system that you would like, provided that you have the waveform. So yesterday, or the day before yesterday, I don't remember, we derived the quadruple formula. And we obtained the expressions for the signal h of t in the frequency domain, quadruple. So now I don't want to rewrite the expression. What this shows you is that for computing the signal-to-noise ratio of a binary system, it's most convenient to do things in the frequency domain. So what you want to do is to take that quadruple strain that we derived and perform a Fourier transform. This, unfortunately, is easier said than done because, well, unless you do the Fourier transform numerically, well, you can certainly do it numerically, but then you have a number of issues with aliasing and so on and so forth. So what we usually, normally, is what we call the stationary, don't worry, I will not go through the derivation, stationary phase approximation. How can I explain it? In 2 words, the stationary phase approximation is very similar to, probably all of you have seen in quantum mechanics the derivation of the group velocity and how that, so essentially when you do the Fourier transform, in order to derive, so if you have a wave packet psi of k ei omega k of t minus kx, this is like a wave packet. You can think of this as a wave function in dk. To derive the group velocity of a wave packet, what you do is actually a Taylor expansion of the phase around a stationary point. The idea being that if the phase varies very rapidly, if this phase varies very rapidly, so here you have so this is psi of k, this function of k, and then if the phase varies very rapidly, this integral cancels. So yes, sorry, this is not a very good drawing, but essentially what you do is to expand the phase near a stationary point, because that's what the integral, where most of the integral comes from, and yeah, and so yeah, so essentially, and that's where you get. So you do I omega k naught prime k naught yes, I don't want to go through the derivations because I didn't prepare, but it's a similar approximation to the one that you get to obtain the group velocity. So you expand essentially the phase near a stationary point. So if you want to know more about this calculation, I think it's an exercise done in one of the Michele Maggiore's books in volume 1. I don't know if you guys know this. It's Maggiore volume 1. It's called Gravitational Waves. And it's an exercise. It takes some time to derive. I mean, and it's done in chapter 4, in one of the exercises after chapter 4. But if you check your quantum mechanics books, you will see that it's very similar to the derivation of the group velocity. But I will not do this. I will just give you the result. So if you take the time domain signal from the quadruple formula that we obtained, you'll find a relatively simple expression for the strain, h of f square root of 5 sixth. This is the chirp mass that Andrea derived or introduced, and that I also introduced a few days ago. And then you have, crucially, frequency to the minus 7/6 over 2 pi to the 2/3 dl. So why dl? This is the luminosity distance, because in general, what we did in the next few days was to expand things around flat space, right? So we only had Euclidean distances. Since LIGO and LISA sources are at cosmological distances, you can't define, there is no unique definition of distance in cosmology. So what you can see is that you can use all the formulae for the quadruple formula, for instance, that we obtained previously in flat space. You can apply them to cosmological settings, provided that you replace the distance to the source, small r, with the luminosity distance, and all masses with what we call redshifted masses, where z is, of course, the cosmological redshift. And in that case, and also the frequency with the observed frequency. This is if you want, maybe for the level of this course it's not needed, but so this chirp mass here would be, well, I never remember what power there is in the chirp mass. Yeah, so m1 times m2 to the 3/5 divided by m1 plus m2 to the 1/5 times 1 plus z. So whenever we say that in gravitational wave physics we measure a certain mass, you have to be careful whether it's what we call the detector frame mass or the source frame mass. The source frame masses are the physical masses, but what we measure in the detectors are these redshifted or detector frame masses. And similarly, the frequencies that we obtained are not the same frequencies at emission, because you have cosmological redshift, of course. You have that the observed frequencies are equal by the frequencies of the source divided by 1 plus z. And similarly, the distance that appears in the waveforms is not the Euclidean distance that wouldn't make any sense in cosmology, but it's the luminosity distance. So why am I telling you all this? I forgot. Yeah, because now, in principle, you could, given this formula, if I give you the sensitivity, given that you buy this phase approximation I'm selling you, from the quadruple formula, you could calculate the signal-to-noise ratio of a source, so you would be able to tell whether a certain source, your favorite source, is detectable by a given instrument or not. Yes, so in fact I have there are some geometrical factors that have to do with the orientation of the detector. So there is a geometric factor here, which let me call Q, is due to this is geometry. And this is what I was telling you the other day, if the binaries face on, edge on, and there are also geometrical factors due to the orientation between due to the fact that the detectors has blind spots. So in particular, if you take the average, if you don't know where your source is in astrophysics, typically you average over sky location and orientation, and this Q becomes, if you average over all that, it becomes 2/5, I think. Yes, 2/5. And of course, this h of f also has a phase. It's not simply a real number, but it has a, let me call it E psi. And psi will also be a function of frequency in general. And well, if you're interested in the explicit phase of this, explicit form of this phase, I can point to you where to find it. So, in fact, I can give you all these expressions in PDF form if you'd like. So, summarizing, we went from the quadruple formula in the beginning of this course we did the Fourier Transform in the stationary phase approximation, and using the optimal filter theorem that we just proved, we were able to compute the signal-to-noise ratio. And in general, this is the proper way to assess whether a source is detectable or not, meaning that you can't just plot your waveform on top of the sensitivity curve. You have to obtain a signal-to-noise ratio which is typically larger than 8. So detectability requires SNR larger or smaller than 8 as a rule of thumb. It depends a bit on the detector and the source. Okay, so the last 20 minutes, in fact, well, maybe I'll give you one more. So if you have a monochromatic source instead, so this is the signal-to-noise ratio for a quadrupolar waveform, you could even ask the question, what happens for a monochromatic source? What is the signal-to-noise ratio for a monochromatic source? Well, and there could be such sources. Certainly there are for LISA. There could be such sources for LIGO in the form, for instance, of isolated pulsars. So h of t for a monochromatic source would be a sine or a cosine. And let me define it as h0 square root of 2, just convention, h naught cosine of 2 pi f plus f prime t minus t naught. This is an almost monochromatic source. It's not a monochromatic source. Plus multiplied by t. So instead of having simply 2 pi ft in the t minus t naught, in the phase, I added also a term that depends on the time variation of the frequency, because in general the frequency will increase due to emission of gravitational waves. So this is an almost monochromatic source, a source whose frequency changes very slowly with time. And then using again the stationary phase approximation, you can prove that h of f, or at least the norm of h of f, equals to the amplitude of the wave divided by 2. This is h of f evaluated at the frequency fc, let me call it fc. So in the end of the day, what you find is that the signal-to-noise ratio for a, did I get, in fact, I'm sorry, I realized now that what I called here, the expression I wrote here for the signal-to-noise ratio is actually the expression for the signal-to-noise squared, I think. And here, yeah, so I either, yes, I'm missing essentially, yeah, square root here, I'm sorry. I realize now. Yeah, okay. Well, you see it from the dimensions. Here I had the square of the signal divided by the noise squared, so I was missing a square root. Sorry about that. So the signal-to-noise ratio for, so let me write the expression, the correct expression. It's the square root of 4 integral from 0 to plus infinity of h tilde f squared divided by Sn of f df, and this is equal to square root of 2 h naught square root of the observation time divided by Sn f to the 1/2. So for in the end of the day, I mean, I didn't prove this, but I can give you, if you're interested, I can give you notes where you can prove it yourself using the stationary phase approximation. This uses the phase approximation, SPA means stationary phase approximation. The signal-to-noise ratio of, in general, a long-lived source, an almost monochromatic source, increases as the square root of the observation time. And and it's proportional, of course, to the amplitude of the source. And this is why, when they do monochromatic searches in LIGO or Virgo, they integrate for a huge, as much as possible. In fact, the main limitation for those searches is the computational resources, because it's very difficult to integrate, to calculate cross correlations. So you need to cross correlate your time series with a template, a monochromatic template, and integrate for years. And this is very difficult to do. In fact, they try to use, well, they use supercomputers, but they also use private users. There is a software called Einstein at Home where you can run these searches, a little bit of these searches when your computer is in an idle state. Okay, so the last 10 minutes, 15 minutes, I will derive the expression for the Fisher matrix that you used yesterday. So far I've only been concerned with detection of gravitational waves. So the signal-to-noise ratio is what the metric we use for detection. So for detecting a signal, we need to have a filter which is as close as possible to the optimal filter. But also we need to, what do I want to say? Yeah, we need SNR larger than a certain threshold, SNR 8. So in order to extract the parameters of the source, we want to make some further assumptions on the noise. So remember, I wrote which I now deleted, the noise is characterized by n of by a one-sided power spectrum, spectral density, delta f minus f prime. Hopefully I have the signs right. Yeah, I think they are correct. So, but I want also to make, so essentially this Sn is the average of the square of the noise at a given frequency. But I also want to make now some assumptions on what is the PDF, the probability distribution of the Fourier transform of the noise. In particular, let me make the assumption that the noise is a Gaussian process. This should be very familiar to those of you who come from cosmology. So what this means, you remember that a Gaussian variable is a Gaussian variable x is defined by 1 over square root of 2 sigma exponential minus 1/2. Well, suppose it's on 0. So what we assume here is that at each frequency, the noise is given by a Gaussian. So the probability of having a Fourier transform n tilde is given by, suppose I can discretize my frequencies, is 1 over square root of 2 sigma of frequency I exponential of minus 1/2 n tilde fi squared divided by sigma squared fi with a product over the whole frequency. So I assume that all frequencies are independent. So what a Gaussian process means is that all frequencies are statistically independent, so they satisfy their own PDF, and then for each one of them, the amplitude of the noise at that frequency is given by a Gaussian law. So now you can write this, well, neglecting, so this sigma f, as I mentioned, you see, for a given function, the norm of, so there is a norm here, sorry, yeah. The ensemble average of the norm of the absolute value of n tilde is simply 1/2 Sn f. So the physical meaning of the power spectral density is simply the sigma, or the RMS, of the noise at a given frequency. So I can rewrite this as, well, forgetting about all factors, which we typically don't care about, this probability for a given realization of the noise in the frequency domain is simply given by exponential of minus 1/2 n cross internal product with n, where this n is given by the same definition that you certainly have in your, let me write it again, the definition of, A and B equals 4 real part from 0 to plus infinity of df A tilde. You don't need to copy this because you probably have it in your notebooks. F, S, N, F. All right. So if you use the fact again that the spectral density is simply the average of the square of the noise, sorry, here I'm missing, of course, this. What you find is that the probability distribution for the noise, under the assumption that the noise is a Gaussian process, is simply given by the exponential of minus n dot n, where this dot is the internal product defined there. So now we'll, how many of you have seen Bayes' theorem? Okay, well, I'll just, for those of you who haven't seen it, I'll just say 2 words on Bayes' theorem. Bayes' theorem is very easy to derive because it's simply composed probability. So I'm certain almost all of you have seen Bayes' theorem when you did the physics lab in order to derive the chi-squared, the chi-squared fit. But Bayes' theorem essentially tells you that the probability, how many of you have heard about the likelihood? Well, same set of people. Okay, maybe not, maybe you haven't seen it. So the probability of the data, let me write this equation and then I will tell you what it is. Probability of the data given the model equal, sorry, the probability that I want to write the other, the probability of data given the model times the probability, the model divided by probability of the data. So if M and D are two assumptions, two logical assumptions, you can write the probability of M and D equals P M given D times the probability of D. Then I will explain what D and M are. And this could also be P of D given M times the probability of M. This is the law of composed probability. And then by combining the two, you get exactly this. This is called Bayes' theorem, but what is the meaning? It means that if you have a certain set of data, D is the data, and the model M, the probability of the model given the data, which is what people usually call the posterior probability, equals the probability of the data given the model, which is what people call the likelihood, times the probability that you assign to the model, which is what people call prior probability, and divided by the probability of having the data, which is what people call the evidence. So what does this mean? Suppose now my model is a set of parameters, like in a square feet, the slope and the offset of my straight line, or in my gravitational wave signal, a set of physical parameters. The probability of a certain set of parameters, let me call them theta k, given the data, this is what I would like to derive. Given the data, certain observation, I would like to understand what is the probability distribution of the parameters. for instance, the probability distribution of the masses, the spins of my black hole, so if I have a gravitational wave observation of a binary black hole system, the probability of the parameters given the data equals the probability of the data, the observation given certain parameters, times the probability that I assign initially to a parameter, divided by the probability of the data. So now, typically, we're not concerned about the probability of having or not having the data, so we're just concerned about the dependence on the parameters, so we write the theorem. This, if you want, is a normalization constant. You can get this evidence by imposing that the posteriors, the probability distribution for the posteriors is normalized to 1. So this is Bayes' theorem. So the probability of the Bayes' theorem, the probability of the parameters given an observation equals the probability of getting the data from those parameters times the probability that we assign to the data and to the parameters in the first place. For instance, if I know that physics doesn't allow for black hole masses less than solar mass, I don't know, I can use a step function for this probability, for this prior probability, so I can exclude already to have very small masses, for instance. But normally what people assume is that P, they are agnostic in most cases, in many cases, and they assume that this is a constant. So they prefer not to make prior assumptions on the parameters. So they set what we say flat priors. So this is what I will be doing here. I assume that this is a constant, so it essentially goes out of this equation. So in the end, what I found is that the posterior probability distribution for the parameters equals the likelihood. So now we want to compute the likelihood and to find the maximum of the likelihood, because the maximum of the likelihood will correspond to the maximum of the posterior, so the most likely parameters for my system. So how do we do that? So I've already written that the output of a detector equals h of t, a signal, plus the noise. And now I know, so the same I can do with the frequency domain. So let me, so for the Fourier transform, so let me write it directly in the Fourier domain. And then I know what is the probability distribution function of a certain Fourier series for the noise. So, and that is simply given by e to the minus 1/2 n pipe n, or however you want to call that internal product. And now I use some complicated mathematics, and I say n tilde equals s tilde minus h tilde. So I just invert this and plug it into this equation. So the probability of, so I get e to the minus, let me write on a different line. So if you want my likelihood, let me call the likelihood lambda of finding the data, so the signal given the parameters. So this is my likelihood. Likelihood, I'm out of chalk again. Likelihood is proportional to e to the minus 1/2, what did I say, s minus h tilde, s minus h tilde, simply by replacing this in there. Okay, so now I expand e to the minus so I now expand this minus 1/2 s. I'll drop the tilde above the the Fourier transforms to simplify the notation. Minus 1/2 h cross h minus plus h dot s, right? Yeah. So now I want to find the maximum of this likelihood when I vary the parameters. So where are the parameters? The parameters are not in the data. S is the data that I measure. The parameters are only here in h. So this h will be dependent on the parameters theta. So in particular, this first term I don't care about because it gives me an overall factor. So I can write lambda I'll just finish this calculation and then we can go to drink coffee. Lambda, so the probability of having a data given certain parameters, theta, is proportional, to the exponential of h theta cross s minus 1/2 h theta, so not cross, of course, pipe or dot theta. Okay, so now I want to find the maximum of this function. Find maximum likelihood estimator. The reason why, you spell likelihood estimator. The reason why I mentioned the chi-squared fit is that if you use exactly, is that the chi-squared fit that you used for linear regression is exactly the maximum likelihood estimator for a model in which your parameters here would be the slope and offset of the fit. And this is a way of introducing the chi-square fit. So this is why the chi-square fit is in a sense, the best fit. Anyway, so without entering into that, if you want to find the maximum of a function, what do? You take you look for the point at which the derivatives are zero. So you take derivatives with respect to the parameters and look for zeros. So what you do here, first of all, you can take the log of the likelihood, because the log is a monotonic function. So the log of the likelihood is proportional to h of, I'm rewriting again the same thing, minus 1/2 h of theta dot h of theta. And you can take the derivatives with respect to the parameters, and you find that the parameters that maximize this log of lambda are those that satisfy this minus di of theta dot h of theta equals 0. Parameters, so theta such that equals 0 are maximum likelihood estimators. So these derivatives here mean derivatives, of course, with respect to parameter, to a given parameter number I. So you look for the maximum of this function, you get the estimator, and then what you can do is not only that, the likelihood, because of Bayes' theorem, is actually proportional to the posteriors. So the posterior you can also get the posterior distribution. I can erase here. Let's see if we can derive the posterior distribution. So we're, again, the posterior, let me call them pi. So the probability of the parameters given the signal is proportional, if you assume flat priors, to the likelihood. So the probability of the data given certain parameters, and we found the maximum of this likelihood, but we want to go beyond that and expand at quadratic order. So if around the maximum likelihood estimator. So I want to write the parameters theta I equals theta I maximum plus delta theta I. Okay? So if I do that, and then I take this, let me do it, log lambda. So we wrote log lambda there is h dot s minus 1/2 h dot h. So now I want to write this h. I want to write it as h of theta maximum plus gradient with respect to parameter I, h theta, evaluated at the maximum, times, what did I call it, delta theta I. So I'm doing just a Taylor expansion. Well, yeah, let's do it. H0 maximum. And I want, in fact, to expand to quadratic order, I'm sorry. Otherwise, it doesn't work, of course. H theta, delta theta I, delta theta j. So I'm just doing a Taylor expansion of the function, of the waveforms around the maximum. Yes, this will have many terms. Well, let's write all of them, it's okay. Plus h of theta plus di h of theta delta theta I plus 1/2 di dj h of theta delta theta I delta theta j dot s. And let me continue on this line, minus 1/2. And here I have the 0th order term. This is maximum. Then I have a minus 1/2. I have 2. I have a 2, so I have minus h maximum times maximum delta theta I. And I'm sorry, I need to go down one more line. And then I have a minus 1/2. Then I have I need to expand this term to quadratic orders. Because it's symmetric, I have another factor 2. di dj h theta maximum dot h theta maximum maximum d theta I d theta j. And I forgot, sorry, here I forgot other terms. Should have corrected me. Yeah, okay, no, I'm just missing one term. Minus, so here, I also have a first order term from here, coupling with a first order term from there. So I get minus 1/2 h derivative of theta delta theta I delta theta j. Okay, let's see what happens. Yeah, so all the terms now should cancel out. So bear with me because they will cancel out, I think. So I have this term. So first, I just expanded this term. So now I'm making an extra assumption. I'm working in the large signal-to-noise ratio system assumptions, SNR much larger than 1. So if SNR larger than 1, S is about the same as H. So the noise is negligible compared to the signal, so I can replace this S with H theta. So now I have let me wait. Finisco gli ultimi 2 minuti, sì. Vabbè, gli do il risultato. Okay, so in the end of the day, what do you get? Log lambda, you get 0th order term in the deviation from in delta theta, so order delta θ0, plus you get orders of delta theta, first order. So those are, yeah, there are a bunch of those terms, but those terms are 0 because you're doing the expansion on the maximum likelihood on the maximum likelihood estimator. Because you're expanding about the maximum, these terms will be 0 because expansion around the maximum. How about the second order terms, which is what we care about? You see that they should cancel out. 1/2. Yeah, they do cancel out. I thought, yeah, they should cancel out, as a matter of fact. Yeah, there is an extra factor 1/2 here. So I have a factor 1/2 from, well, if you look at my notes, you have an extra factor 1/2 here. So this term should cancel out, the second derivatives of h should cancel out with those of that term. And in the end of the day, what you'll get is the only term that survives is the exponential of minus 1/2 gamma ij delta theta I delta theta j, where this gamma ij is nothing but the derivative of h with respect to parameter I dot the derivative of h with respect to parameter j. This is what we call the Fisher matrix, and this is the last thing I will Fisher matrix. So maybe I'll say, because we're already late, I'll say a few words about this Fisher matrix this afternoon before I start. But essentially, you can see already that we found the PDF. Well, in fact, there is no exponential because I took the log here, or let me take the log off here. The likelihood, and therefore the posteriors, now take a Gaussian form. So they're the exponential of a quadratic function. And so this Fisher matrix, which you can compute from the waveforms by taking derivatives of the waveform with respect to the parameters, is nothing but the inverse of the covariance function of the parameters. So the derivation is essentially done, but since we're late, I'll say 5 more minutes this afternoon about this. Well, thanks, and have a nice coffee.